So the second example considers a pressure vessel. So imagine we have a cylindrical pressure vessel. So it's a thin-walled pressure vessel. There's some pressure on the inside. First of all, we're going to calculate the stress state, and then we're going to calculate the strains in the pressure vessel. And part of the reason I wanted to do this example is that the second lab involves a pressure vessel. We take Coke cans, basically, and we have a little fixture on the end of the Coke can, and we pressurize them, and you put strain gauges on the Coke can, and then you can measure the strains. And we're going to use Hooke's law to then figure out what the stresses are and relate that to the pressure. So we have a little doodah that we can increase the pressure in the can, and you're measuring the strains, and the strains increase, and you're going to measure the strains in different directions. So this is really of relevance for the second lab that you do later on in the term. Okay, so we're going to consider the thin-walled cylindrical pressure vessel. And when we say thin-walled, what that means is the radius r is going to be a lot thicker than the wall thickness t. And the vessel has an internal pressure I'm going to call P. And the question is, what are the stresses in the wall and what are the strains in the wall? Okay. So here's our pressure vessel here. It's a cylinder. It's got a radius r like that, and the walls are small. The wall thickness is small compared to r. So first of all, I want to calculate the stresses, and I need to make a little free body diagram in order to do that. And what I'm going to do, first of all, is make a cut here. We'll call that AA. And we're going to look at the cylinder end on, and we'll do a free body diagram. So if I do that, here's my little piece of the cylinder, and say I've cut it like that. There's the cylindrical opening. Okay. And there's going to be some stress in the longitudinal direction like that in the wall. So I'm going to call that sigma L. And that's going to be opposed by a pressure P inside. So that stress is going to be put the wall in tension, and the pressure is going to be pushing on it. And those two stresses are going to balance out. Okay? And the forces from those two stresses are going to balance out. So the force is the longitudinal stress times the area that it's acting over. So this longitudinal stress is acting over the wall thickness there. So the area is 2 pi r times the thickness. Okay? Yes?
I'm a little bit confused. I guess just from pressure, I would think that the stress would be like normal to the wall, but why does it look like it's going along?
It looks like it's going along because I've drawn the longitudinal stress. But there is a radial stress. We'll get to that. There's going to be 3 stresses. We're going to get to it. Will you just believe me?
I'm just confused with the longitudinal stress in this one.
Oh, so imagine I slice the cylinder right here. Okay, you could believe there's a pressure going that way, couldn't you? No, the pressure. So the pressure in the cylinder is going to act basically in all directions. So there's going to be a pressure acting that way, and that longitudinal stress is going to oppose that pressure. The forces from those two are going to balance out. Are we good? Is everybody else good? Yeah. Okay. So the force that corresponds to this longitudinal stress in the wall is sigma longitudinal times 2 pi RT. And the force from the pressure is going to act over the whole area, so it's going to act over pi r squared. So the pi's are going to cancel out. One of the r's is going to cancel out. And we're going to find the longitudinal stress is just PR over 2t. So whatever P is, remember R over T is a big number, so it magnifies the pressure by some large number, because R over T is big. So now I'm going to make a second cut. So now let me glue this back together this way on. So I glue that back together. And now I'm going to make a second cut this way on. And we'll call that BB. So this is the cut BB. And we're going to have some thickness of the wall. It's like I've cut the cylinder, you know, in half this way. So say my chalk was the cylinder, it'd be as if I cut it right down the middle there. Okay, but imagine it's hollow. So this time we're going to have some stress that comes, that's called a hoop stress. So this is a stress that goes basically around the thing, around the wall. So the hoop stress is going this way and this way and this way and this way, kind of working its way around. Okay, so it kind of goes around like that. So there's another hoop stress there. So we're going to call that sigma h for the hoop. And then there's going to be a pressure pushing against that this way. And it's hard for me to show it, but let me just say there's a pressure that way. So then we'll say the same sort of force balance. We've got this hoop stress. Say this is a length here, L. So that acts over a length L and an area, a thickness T. And there's 2 because there's one at the top, one at the bottom down there. And that's going to balance. The pressure is going to act over L times 2R. Yeah?
Professor, for cut AA, I don't quite see how the pressure acts across an area of pi r squared. Like, isn't it just empty space, pi r squared?
So think of, you can think of the pressure as hitting like the end of the wall. So imagine I've got my cylinder, it's got some end here, and I've cut it in half here.
Oh.
Imagine that the pressure's on that end of the wall.
Oh, okay.
And then, in fact, it has an equivalent force of P times the pi r squared. Are we good? Are you now good?
Yeah.
Okay. 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 And I know my drawings leave something to be desired, but do you see what's going on here? We take the cylinder, we cut it this way. Imagine it had it's hollow here. There's a stress in the wall that sort of, if I looked at it at the top, it would go that way, and the pressure is pushing against the thing like this. You're good? Everybody else? Okay. So I've got the hoop stress times the length times 2 thicknesses, because there's 2 walls there. And I've got the pressure times the length times the 2R. So the pressure is acting over that thing there. So the factors of 2 cancel out. The L's cancel out. And here we have that the hoop stress is PR over T, like that. Okay? Are you happy, Rachel? You look very skeptical. You're not happy. What's wrong?
About what the pressure's acting on in this case. I understood what you just said about a lot of
okay. So imagine the pressure's pushing on the back wall. The pressure's pushing on the back wall, and the back wall's curved, but if you calculated the force that it was equivalent to, it would just be the projected area, which is the L times the 2R.
Okay.
Yeah? Are you humoring me, or you believe me?
I believe you.
Okay.
It's a little weird.
Yeah?
I believe you.
The hydrostatic stress agent, what that is,
That's not hydrogen.
Okay, so the pressure actually is, it's a uniform stress in all 3 directions. So the pressure in the cylinder, it acts equally, you know, the pressure you could say has a sigma x component equal to P, a sigma y component equal to P, a sigma z component equal to P. Okay, so that pressure is, it's like a normal stress that's equal in all directions.
So are you using the capital H to denote hoop, or to
I am.
denote hydrostatic? Or
Oh,
both?
no, oh, sorry, sigma, capital H is hoop.
Okay.
So it goes around the circumference. Sigma little h is what I used for hydrostatic. Are we all good? Okay. Yes, in the back?
So back to the cross-section with the circle. So then on the left side, so why isn't it like 2 pi r plus t?
Because I'm saying small. And if it's thin, then t is small compared to r, and I can just say it's 2 pi r times t is the area. Okay? It's thin-walled. There's different equations for thick-walled that are more complicated. That's why we're not doing thick-walled. We're doing thin-walled. Okay? Okay. So that gives us a stress. And so one of the things to notice is that the hoop stress is twice the longitudinal.
Another question, this time along cut BB.
Sorry?
This time it's along the cut BB. So,
The cut BB. Okay.
so when you look at the area that the pressure is acting on, isn't it this inner surface?
Sure. So it is the inner surface. So say this is my tube like this. Okay. So here's the hoop stress is acting here and here. Oops, let me make my tube more cylindrical. Okay. So the pressure is on this back wall, but the equivalent force is that pressure times this projected area. If you took fluid mechanics, you would get that. And since you haven't taken fluid mechanics, I'm just telling you that. Okay? So the pressure has a force equivalent to the pressure times that projected area. Well, I mean, the cylinder does have a circular area, but it's the projection of that. Okay? Okay. And the same as it acts, you know, on cut AA, I can't make my paper do this, but say that was the end, the left end. It's acting on that curved surface, but the equivalent force is on that projected area, which is the pi r squared. Okay, okay, okay. So but let me get back to the point. The point is that the longitudinal stress is PR over 2t, and the hoop stress is PR over t. So the hoop stress is always twice the longitudinal stress. Okay? So the hoop stress is the biggest one. And someone asked, what about the stress in the third direction? And there is a radial stress too, and we can have a look at that. Whoop. Yeah?
How do you like tell how many different stresses there are just by looking at that?
So we're looking at sort of a Cartesian set of stresses. So you might look in 3 normal directions, and then you would kind of say, what are they in the 3 normal directions? Okay. But we're going to find out that the radial one is so small, we're going to forget about it. Yep. Okay, let me get to the radial stress. Okay, so there's a radial stress sigma r, and at the inner wall, sigma r is just going to be equal to p. So you think of the radial stress, so think of my cylinder here. Oops, here's my cylinder. So the radial stress is, you know, going like this. And the pressure is also going like that. So at the inside wall, the radial stress just is the pressure. And at the outer wall, the radial stress is just 0. Okay, so it just dies out to 0. And you can see if these two stresses here are P times R over T, and we said it's thin-walled, so R over T is big, these stresses are always going to be a lot bigger than the radial stress, and so we're just going to neglect the radial stress. Okay? Okay, so are we good with neglecting sigma r, the radial stress? So it's going to be equal to P at the biggest, and the other ones are much bigger than P. Okay. So let's see. So the last thing I want to do is to calculate the strains. And in particular, I'm interested in the ratio of the hoop strain to the longitudinal strain. So we can get these strains by just using Hooke's law. Okay, so the hoop strain is going to be the hoop stress over E minus nu times the longitudinal stress over E. The hoop stress was just PR over T, so I divide that by E. This is going to be PR over 2T, so it's going to be 1 minus nu over 2, like that. And then the longitudinal strain, you just flip them around. You've got sigma L over E minus nu times sigma H over E. And you can get that expression there. And then if I take the ratio of the two of them, I get that. And so if Poisson's ratio is a third, or let me, actually if it's a 0.3, not a third, boink. If it's 0.3, then the ratio of the two strains is 4.25. So even though the ratio of the stresses is 2, the ratio of the strains is not 2. Yeah?
Is there a reason why the ratio of the strains?
It's not 2?
I mean, is there a reason why we look at the ratio of the strains?
Because when you do the lab, you're going to measure the strains. And the thing I find in the lab is that people look at the stresses and they see the ratio of 2 and they think the strains must also be in the ratio of 2. It's a different ratio. And you get that ratio by using Hooke's law. Okay?